Imagine you're driving down the highway at, like, 80 miles an hour.
Okay.
And a microscopic grain of sand suddenly causes your entire engine block to just violently explode.
Yeah, which sounds like a totally bizarre hypothetical, right?
Right. I mean, in the everyday world, it makes no sense. But if you step into the world of high-speed aerospace or, medical
Oh,
manufacturing,
absolutely.
the places making jet engine parts or titanium bone screws that you might actually rely on one day, that scenario is basically a daily reality.
It really is. It's a phenomenal study in how physics just amplifies tiny errors.
Exactly. So today, we're doing a deep dive into a highly technical manual on tapping centers.
And for those who don't know, these are hyper-precise, incredibly fast, computer-controlled machining tools.
Yeah, and our mission here is to decode the surprising truth hidden in all these dense engineering protocols.
Yeah.
We want to figure out how these, microscopic, seemingly invisible oversights during setup can cause massive, violent machine failures.
Because a tapping center is operating at tens of thousands of revolutions per minute.
Right.
I mean, we're not talking about a smudge that just makes the machine look dirty.
Right.
We're talking about foundational instability.
Right.
That leads to oversized cuts, shattered tools, and literal machine collisions that can, destroy a whole production schedule.
Okay, let's unpack this with a mental image for everyone listening. Think about running a marathon.
Oh, I love this analogy.
Yeah. So if you have a tiny, almost microscopic grain of sand in your running shoe and you're just walking down your driveway to check the mail.
You don't even feel it.
Exactly. The impact velocity is way too low. But if you're sprinting at top speed over 26 miles, that tiny grain of sand fundamentally changes your gait. It grinds into your skin and eventually wrecks your foot.
And a tapping center operates on that exact same principle.
Yeah.
Just, with solid steel and extreme rotational velocity. That marathon analogy perfectly captures the core theme of the technical documents we're looking at today. A stable machining process absolutely does not start when the operator presses the start button.
Wait, it doesn't?
No, not at all. Precision is 100% dependent on what happens before the tool ever even touches the metal.
Wow, okay.
Yeah, if the foundation, like the literal physical connection between the machine and the cutting tool, is flawed by just a fraction of a millimeter, high-speed rotation mathematically multiplies that flaw.
Which means the first hurdle we really have to clear is, this invisible enemy? Dust.
Dust, yep.
The source material establishes this golden rule right out of the gate. Where there is dust, there is error.
It's so true. And if you're reading along with us, you'll see this concept tied to a mechanical principle called radial runout.
Right, so let's break down exactly how dust causes this radial runout. Let's start with the physical connection itself.
Sure, so the machine spindle, that's the part that actually does the spinning, and the tool holder connect using a tapered shape.
It's essentially like a perfectly machined cone fitting inside another perfectly machined cone.
Exactly. And that connection relies on skin-to-skin contact. The engineering term for it is a flush mate.
A flush mate, got it.
Yeah, so when a tapered tool holder is pulled up into the spindle, those two angled steel surfaces must mate perfectly. That ensures the cutting tool is pointing absolutely dead straight.
Okay, but imagine a single metal chip, or even just a thick film of cutting oil sitting on that taper.
Right. When the machine clamps down with thousands of pounds of force, that tiny chip prevents the cones from seating evenly.
So the holder is forced to sit ever so slightly crooked.
Yep, which means the center line of the tool is no longer perfectly aligned with the center line of the spindle.
And because the tool sticks out from the spindle, a microscopic tilt at the base becomes this massive wobble at the tip, right?
Precisely. That wobble is the radial runout.
Oh, okay.
And when you introduce that wobble to a milling cutter spinning at, say, 20,000 RPM,
Yeah.
the cutting edge isn't slicing cleanly anymore.
It's biting into the metal super aggressively on one side and then barely touching it on the other side of the rotation.
Exactly. And that uneven force generates aggressive vibration. It's known as chatter.
Chatter, right. And that leaves those deep, ugly ripples on the machine's surface, right?
It does. It bores holes that are totally out of tolerance. And it subjects the cutting tool to such severe lateral shock that the carbide edges will microchip and dull almost immediately.
It's really tempting, especially if you're someone who fixes things around the house, to think you can just brute force a cleaning solution here.
Oh, for sure.
Like if I'm looking at a machine coated in fine metal dust and oil, My first instinct is to grab a compressed air hose and just blast it.
Oh, yeah, just blow it all away.
Yeah, or I don't know, dump a bunch of industrial solvent all over it.
Yeah.
But the text explicitly warns against those standard shop instincts.
Because those high-power solutions actively weaponize the debris.
Wait, weaponize it? How?
Well, think about it. If you blast high-pressure air directly into the open spindle taper, you're not vaporizing the chips, you're turning them into high-velocity projectiles.
Oh, wow.
Yeah, and you're driving them upward into the spindle's internal gripper mechanism. Those are the intricate mechanical fingers that actually grab the tool.
And I'm guessing you can't exactly reach in there to clean those out.
Not at all. Plus, you're aerosolizing the cutting oil and the fine dust, spreading this mist of contaminants across the entire facility.
Okay, so air is bad, but what about flooding it with solvent? That creates a totally different kind of permanent damage, right?
Yep, the huge issue there is residual moisture.
Ah, of course.
If you douse that precision ground taper in fluid and fail to dry it perfectly, the trapped moisture creates microscopic oxidation. Basically, rust.
And rust is the absolute death of a flushmate, as we called it earlier.
It really is. Once that taper rusts, the surface becomes pitted. You completely lose that smooth geometry.
And replacing a high-speed spindle cartridge is, what, an incredibly massive expense.
Oh, massively expensive. So the protocols demand a surprisingly low-tech but highly deliberate alternative.
Right. The manual says it requires wiping the contact surfaces manually with a clean white cloth
Okay.
or a specialized non-woven fabric.
Exactly. It's a meticulous visual inspection. You wipe the taper, you verify there's zero oil film, zero dust, and you ensure it's perfectly dry.
Okay, so let's say we've done that. We have a pristine, dust-free environment. The taper is clean,
Great.
but our sources make it really clear that a clean connection to the machine is basically useless if the mechanical grip holding the actual cutting bit is flawed.
Right, which brings us to the assembly phase, specifically collet selection.
So for the listeners, a collet is that slotted steel collar that squeezes down on the cylindrical shank of the cutting tool.
Yep, and the documentation is super rigid here. If you have a 10-millimeter milling cutter, it demands exactly a 10-millimeter collet.
Which sounds incredibly obvious, I know. But the text specifically highlights this dangerous practice of operators trying to force mismatched sizes.
Oh, it happens all the time. Like trying to clamp a 6-millimeter tool in an 8-millimeter collet.
Here's where it gets really interesting, though. Trying to do that isn't just a matter of the tool feeling a bit loose. It's literally like trying to hold a wet bar of soap by just pinching the very edges.
That is a great way to picture it.
Right. The moment any upward cutting pressure hits that tool, the mechanical grip just fails. The contact area is totally compromised.
Exactly. The gripping force isn't distributed evenly at all. When that mismatch occurs, the cutting resistance actually pushes the tool backward.
So it slides up inside the holder.
Yep, forcing it up, and suddenly your programmed depth of cut is totally inaccurate.
And beyond that, the uneven grip allows the tool to pivot microscopically within the collet, right?
Yes, and that pivoting causes violent vibration. It will either scrap the incredibly expensive aerospace part you're machining or just snap the cutter entirely.
Oh, man.
And in the process, you've permanently deformed the internal bore of the collet itself.
So even if you do select the correct size, the mechanical design of these systems has this sort of trap for the uninitiated.
Oh, the ER collet system.
Yes. The ER collet system, which is everywhere in manufacturing, has this non-negotiable order of operations. The collet actually has to snap into the clamping nut before that nut is ever threaded onto the tool holder.
It's such a brilliant quirk of mechanical engineering, honestly.
How does it actually work?
Well, inside the clamping nut, there's an eccentric extractor ring. Its whole job is to physically pull the wedged collet out of the holder when you loosen the nut later.
Okay, so if you just drop the collet into the holder first, and then try to thread the nut over the top.
The extractor ring never engages the groove on the collet.
Oh.
Yeah, it won't seat properly to clamp. And worse, when you try to take it apart later, the collet will be hopelessly jammed inside the taper.
So you have to insert the collet into the nut at an angle, press it until you feel and hear a really distinct mechanical click.
Yes, that click is crucial. And only then do you screw the assembly onto the holder.
Okay, so once it's clicked and threaded, we have to figure out how far the cutting tool should stick out.
Right, the extension length.
You obviously need enough length to reach the bottom of whatever feature you're machining, but you can't just leave it dangling way out there.
No, definitely not. The engineering rule of thumb provided in the source is the 4x rule.
The 4x rule. meaning the unsupported extension length of the tool should never exceed 4 times the diameter of the tool's shank.
Exactly. It's a pure physics calculation based on leverage and rigidity.
Right.
Any cutting tool is essentially a cantilever beam.
Hmm.
When you apply lateral force to the tip of that beam during a cut, the beam wants to deflect or bend.
So if a tool overhangs too far, it completely loses its structural rigidity.
Yep. Which brings us back to the chatter we discussed earlier.
Right, because the tool is microscopically bending away from the metal, springing back, and then biting in again like thousands of times a second.
Precisely. And that deflection shatters those brittle carbide cutting edges.
So the standard operating procedure is to maximize the clamping length inside the holder for optimal grip.
Yep, leaving only the exact amount of flute length exposed that's absolutely necessary to complete the cut and evacuate the metal chips.
Okay, so we've got the proper extension, the collet is clicked in, now it's time to apply torque and lock it down.
Here we go.
And again, if you read the source notes, there is a massive warning label about how you actually hold this assembly while tightening it.
A huge warning.
Because, I mean, it's super tempting to take this precision holder, walk over to the heavy steel bench vise in the corner of your garage or shop, clamp it tight, and just crank on it with a big wrench.
Oh, please don't do that.
Right.
If we recall the absolute necessity of that pristine taper we talked about during the cleaning phase,
Yeah.
clamping this tool in a bench vise is a catastrophic error.
Because a standard bench vise has those hardened, grooved steel jaws.
Yes, if you crush a precision ground tool holder between those jaws, you are instantly scratching, denting, and galling the positioning surface.
You're artificially manufacturing the grain of sand from our marathon analogy.
That is exactly what you're doing. You're creating a permanent ridge of deformed steel that will forever prevent that holder from seating flush inside the spindle.
You've completely destroyed its concentricity.
Completely. The protocol mandates the use of a professional tool locking fixture.
And those fixtures are engineered with really specific geometries, right?
Right. They often use roller bearings or precise mating tapers to securely grip the holder by its non-critical flanges.
Ah, so you can apply high torque without ever actually touching the precision taper.
Exactly.
Okay, so as we move from standard mechanical clamping to actually loading the machine, the interlocks get even more complex.
Oh, definitely.
Let's talk about the BT taper system from the text. You aren't just pushing a cone into a hole here.
No, it's way more involved. There's a pull stud at the very top of the holder. It looks kind of like a mushroom-shaped knob. The machine's internal drawbar drops down. Its mechanical claws grab that pull stud, and then it retracts upward with immense hydraulic or pneumatic force.
But wait, there are also these heavy steel blocks on the face of the spindle, right? The drive dogs?
Yes, the drive dogs. Those must slot perfectly into the corresponding notches or keyways on the flange of the tool holder.
And those are what actually transmit the heavy rotational torque from the motor to the tool?
Right. So if you're manually loading a BT holder, you have to align those keyways by hand.
And if you twist it eccentrically, the drive dogs hit the flat face of the flange instead of dropping into the slots.
Yep. And if you hit the clamp button while it's misaligned like that, the drawbar will try to pull it up, but it'll just be jammed against the drive dogs.
So the holder won't seat.
It won't seat, which leads to massive runout. But more importantly, it sets a trap for the machine's automation, which we'll get to in a second.
Right. So for the manual load, the human element requires tactile and auditory confirmation.
Absolutely. You support the tool, actuate the clamp, and listen for the distinct, heavy mechanical clunk of the grippers engaging that pull stud.
And then you give it a firm downward tug just to verify the retention force.
Exactly. Because a clean tool is great, but it's useless if the mechanical grip or the seating is fundamentally flawed.
So true. Okay, let's pivot to the really advanced side of the industry. The notes transition us away from wrenches and collets entirely and get into thermal dynamics.
Heat shrink holders.
Yes, heat shrink holders. Instead of a slotted collet crushing down on the tool, this system uses the coefficient of thermal expansion to create a unified mass of steel and carbide.
It's amazing. The engineering behind heat shrink technology is elegant, but it's entirely unforgiving.
How so?
Well, the bore of a heat shrink holder is manufactured to a diameter slightly smaller than the cutting tool itself.
Oh, so at room temperature, it's physically impossible to insert the tool.
Exactly. You have to apply an intense, localized heat source, usually a highly calibrated magnetic induction heater, to the nose of the holder.
And the steel rapidly absorbs that thermal energy and expands, opening the bore just enough to drop the cold cutting tool inside.
Right. And as the steel cools, it shrinks aggressively back toward its original dimensions.
Creating this massive, uniform 360-degree clamping force around the tool shank.
Yes. Because there are no moving parts, no nuts, and no collets, the radial runout is nearly non-existent. It really is the pinnacle of precision clamping.
But the thermal balance is a razor's edge, right? Like, what happens if an operator overrides the heater settings and overheats the holder to try and make the tool drop in faster?
That is a huge mistake. You introduce permanent metallurgical damage.
Wow.
Yeah, steel has an elastic memory. It can expand and contract repeatedly if it's kept within a specific temperature threshold.
But if you go over that,
If you overheat the steel, it loses its temper. The actual crystalline structure of the metal fundamentally changes.
so when it cools, it won't shrink back fully.
Exactly. The holder has permanently lost its gripping force.
Which means during a high-speed milling pass, that cutting tool can just simply pull out of the bore, plunge right into the aerospace titanium you're machining, and instantly destroy the part.
Yep. Or you fall into the reverse trap, underheating.
Oh, right. What happens then?
If the induction cycle is too short, the bore doesn't expand adequately. So as you try to slide the cold carbide tool into the holder, the steel begins cooling and shrinking prematurely.
Oh, so it just gets locked in place.
Hydraulically locked halfway down the bore before reaching the proper depth. It's totally stuck, and the tool length is entirely compromised.
Which perfectly transitions us to the automated side of the equation. Because whether you're using an ER collet or a perfectly shrunk thermal holder, these tapping centers rely on super aggressive robotics.
They do. They have external magazines holding dozens of tools.
Right, and a robotic arm swaps them in and out of the spindle in fractions of a second.
But that speed requires blind faith from the machine's control system. The robotic tool changer operates with extreme velocity and absolutely zero hesitation.
It just assumes the physical reality matches its programming flawlessly.
Always.
So you might be wondering, why can't we just rely on the robot arm sensors to catch an error? Like, what happens if that tool holder flange is dented from our forbidden bench vise, or there's a chip of metal stuck to the V-groove, or the robot grabs it?
Well, the robotic arm attempts its high-speed transfer, but the geometry is wrong.
Right.
In a best-case scenario, the servo motors detect a spike in resistance, the machine throws a fault alarm, and production halts.
Okay, so a costly delay, but at least it's safe.
Right. But the worst-case scenario involves the mechanics we discussed earlier, like those keyways and drive dogs.
Oh, no.
Yeah. If a tool is seated improperly in the magazine, or if the keyways are misaligned when the robot attempts to jam the holder into the spindle, the collision is catastrophic.
Because the spindle, moving downward with incredible force, crashes into an unyielding steel object.
Exactly. The robotic gripper fingers shatter. The tool magazine pocket is just ripped apart.
You're basically looking at a maintenance nightmare that requires realigning the entire tool change geometry of the machine.
Costing days of downtime and tens of thousands of dollars.
Okay, so we've navigated the physical minefield, we wiped the dust, clicked the collet, avoided the bench vise, respected the thermal expansion, and ensured perfect alignment in the magazine.
The physical work is flawless.
But if you look at the final section of our source documents, there's still a massive gap remaining. The machine's brain, the CNC control software, is completely blind to everything we just did.
This is the critical translation phase. The control software only executes mathematical commands.
Right.
It does not know how long the tool actually is until you tell it. You must bridge the gap between physical reality and digital processing using tool offsets.
And the primary data point here is Z-axis tool length compensation, right?
Yes. The machine knows exactly where the bottom of its spindle is in three-dimensional space, but it has no idea how far the cutting tip extends below that spindle.
So, if an operator loads a drill bit that extends, say, exactly 100 millimeters from the spindle nose, but forgets to input that data into the control's offset registry.
The machine assumes the tool length is 0.
Oh, wow.
Yeah, it will drive the spindle downward until the spindle nose reaches the programmed coordinate, completely ignoring the 100 millimeters of solid carbide sticking out of it.
So it'll just plunge that tool straight through the workpiece and into the machine table?
Exactly. It's a disaster. And the machine also relies on tool offset numbers, which link the physical pocket in the magazine to a specific line of code.
Right, so if you put a heavy face milling tool in pocket number 5, but the program calls up the length offset for a tiny, delicate engraving tool.
The machine confidently executes the code using entirely wrong spatial parameters.
It'll either cause a violent crash by plunging a huge tool way too deep, or it'll just cut aggressively through empty air above the part.
Yep, which means after all this meticulous setup, an operator never, ever simply presses cycle start and walks away.
Trusting the data blindly is a recipe for disaster.
Totally. The text establishes a rigid verification protocol. A safe dry run is mandatory.
Okay, what does that involve?
It involves running the program toolpath in the air without a part loaded, or using a single block check where the operator forces the machine to read and execute the code one single line at a time.
So you basically watch the physical motion path and visually confirm that the tool is going exactly where the math dictates it should go.
Exactly. And even if the air cut looks perfect, you still execute a first piece inspection.
You machine one single component, halt the process, and take that part to the quality lab to measure every critical dimension.
Yes. Only when you prove that the clean taper, the correct collet, and the precise offset numbers have resulted in a part that perfectly matches the blueprint. Only then do you authorize a continuous production run.
Because skipping that check risks automatically manufacturing hundreds of pieces of expensive, useless scrap metal.
It's a profound chain of custody. Precision is not just a feature of the machine you buy. Precision is the result of unbroken discipline at every single physical and digital intersection.
I think if you're joining us today to understand complex systems, whether that's in manufacturing, software engineering, or even aviation, this deep dive really provides a perfect blueprint.
It really does.
The massive catastrophic failures rarely stem from a flawed design. They stem from the overlooked microscopic details.
The skips wipe with a cloth.
The mismatched collet.
The unverified offset number.
Exactly. Foundational stability dictates large-scale success.
And, if we project these source documents into the future, it raises a fascinating question regarding that human element.
Oh, definitely.
Right now, the burden of perfection relies entirely on the operator's discipline to wipe the taper and feel the collet click.
Right.
But as technology rapidly evolves, how close are we to developing truly smart tapping centers?
Oh, that's interesting.
Imagine a spindle equipped with integrated microsensors that can continuously monitor radial runout at the nanometer level, or laser arrays that automatically scan and verify tool links before the spindle ever turns on.
Wow.
We are on the precipice of engineering the fragile, error-prone human element out of the setup equation entirely.
Will the marathon shoes of the future have microsensors that detect and eject the grain of sand before we ever take a step?
That's the question.
It's a brilliant thought to leave on, but until those systems exist, we have to remain vigilant and keep checking our own foundational stability. Thank you for taking this deep dive with us today. Keep questioning the hidden mechanisms in the world around you, and we'll catch you next time.